All right, hello and welcome to class. There's a couple things I'd like to show you on the Moodle page. So right now I'm on the meta shell, and I've just taken the time to revamp the meta shell just to update the meta shell and have it look a little bit better. So here's the Zoom link for the class. I've noticed that we're kind of missing a couple people, so we only have 16 participants today. So I'm wondering where is everybody, but that's all right. I guess they'll either watch the video afterwards, or I've already posted the lecture from yesterday, so perhaps that's what they're watching instead. So I'm sharing my screen right now, and I'm on the meta page, and I just wanted to let you know that it's been updated. So a little bit about the instructor, so that's myself. A little bit about the course, so the course outline, the course syllabus. This is really important for you to know about the course syllabus. This gives you a summary about what is due and when is due, when it's due. So it gives you a week by week breakdown as to what is going on. So this is week number 4. So this is what we're going to be discussing today. We're looking at chapter 3. So in case you want to read ahead, and a quiz number 2, which was due yesterday at noon, as far as I can remember. And then we're going to have week 5. The exam is coming up. It's actually on, next week. So next week there's going to be, is that the exam is next week? It's actually on Wednesday, February the 10th. Let me just check my calendar here. So that, next Wednesday, there's going to be an exam. So, so let me get you prepared for the exam. Today, we're going to be discussing all the concepts that are going to be on the exam. So it's really important that I get to the content today. So another thing pertaining to the exam, in terms of getting you ready for the exam, so I'll click on the meta page and I'll go straight to the assessments. So if you click on the exam outline, this will get you to everything that's going to be on the exam. So definitions, there's going to be 4 marks on nominal, ordinal, ratio data, interval data, those kind of definitions. Frequency distribution tables, cumulative relative frequency distribution tables, graphing. There's different types of graphs like the histograms, the dot plots, the time series plots, the shape of the distribution as in skew, left skew versus right skew, the measures of center, mean, median, mid-range, and mode. So you're going to have to know how to calculate all of those. The measures of variation, calculating standard deviation and variance for raw data. So that all comes with a formula sheet. The measures of relative standing. So we're going to talk today about the 5-number summary, where the minimum, Q1, Q2, and Q3, and the maximum. We're going to talk about interpreting box plots today for skew to identify min, Q1, Q2, and Q3. It's a question in the chat. Yeah, I'm going to record today's class. Yeah, today's class is being recorded. It's already being recorded, and it'll be posted later. Okay. Actually, yesterday's class was recorded and it is already posted. So it's posted. I'll show you where it is posted. So this is the formula. Sorry, that's the outline. And that's something that I would study. I would study all those topics on it because it actually gives you a breakdown of all the questions that are going to be on the exam. So that's the best advice I can give you. The formula sheet is something I would get accustomed to. So the formula sheet is what you'll have on the exam. And it's these formulas right here at the top left. Those are the formulas that I'd be most familiar with because those are the formulas that you're going to be using on the exam the most. Okay. And I'll show you where today's lecture is, or yesterday's lecture is already recorded and it's posted right here. So there's plenty of, there's actually a breakdown of, of the concepts of yesterday. So I might even post today's lecture as well. Is there going to be an exam review? Perhaps the tutorial could actually be an exam review. So this upcoming tutorial this week, I could actually break down some of those concepts in the tutorial. Okay, let me just fix my headphones here. All right. So what is the format for the exam? Will it be multiple choice or we make it on Excel? So the questions of the exam will be like create a histogram for the following data, or interpret the following graph, or find the median of the following data, or find the mid-range or mean, median, and mode of the following data. So it's going to be like questions that you'd see in your homework, those types of questions. All right. So with that, I think I should probably get started on today's information since it is on the exam. So I'm going to get started with that. Okay, so let's talk about measures of variation. That's where we are in the textbook, is chapter 3.2 and 3.3, measures of variation. What is variation? Variation refers to how spread out the data values in a particular data set are. Data sets with a narrow range have low variation. Example, blood potassium levels. Data sets with a very broad range have high variation. Example, income in dollars. Variation can be expressed as range and sample standard deviation, lowercase s. Sample standard deviation is represented by the Greek letter sigma. Variation with reference to the mean. High variation means the data is more spread out around the mean. Some measurements are very far from the mean value. The mean average or average is less mean. Yes?
Are you supposed to be screen sharing?
Oh, yes. Okay, so these notes are posted in Moodle, but yeah, I am supposed to be screen sharing at the moment. Thank you. Okay, so variation with reference to the mean. High variation means that the data is more spread out around the mean. Some measurements are very far from the mean value. The mean or average is less meaningful when there is high variation in the data points. Low variation means that most of the data points are very close to the mean. Okay, so here we have high variation in the treatment, where the pulse rate is, where all the data values are spread out and there's high variation. And in the placebo, there is low variation and the data points are very close to the mean. The mean being the value directly in the middle of the normal distribution, which would be 70 in this case. 70 would be the mean here. The range. The range is the difference between the minimum and the maximum values in the data set, and it's sensitive to skew and outliers. Quick to calculate, but not particularly accurate measure of variation, but not a particularly accurate measure of variation. The range is equal to the maximum data value minus the minimum data value. The following data sets include the heights of inches of 5 starting players from 2 different basketball teams. Here we have the Cleveland Cavaliers and the Golden State Warriors. Calculate the mean for each data set. Okay, so the mean, we know from our formula sheet, if we zoom in, we know the mean is x bar is equal to the sum of all x's divided by n, or the number of data points we have. So here we have the mean is equal to the sum of all x's divided by the number of x's. So 77 plus 78 plus 79 plus 80 plus 81. And then we divide by the number of data points we have. So the number of data points we have is equal to 5. So this is equal to 77 plus 78 plus 79 plus 80 plus 81 is equal to 395 divided by 5. So 395 divided by 5 is equal to 79. So that means our average for the Cleveland Cavaliers is 79 inches. Or, whoops, 79. I don't know why I wrote 91. 79 inches. Okay. For the Golden State Warriors, the mean for this data set is 71, whoops. Right, so we're going to use the same formula. The mean is equal to the sum of all x's divided by the number of x's. This is equal to 71 plus 77 plus 79 plus 84 plus 84. It's equal to 395 divided by n, or the number of data points that we have, which is equal to 1, 2, 3, 4, 5, 5 basketball players. So we have 5 at the bottom. So 395 divided by 5 is the same as above, which is equal to 79 inches. Calculate the range for each data set. So the Cleveland Cavaliers, the range is equal to the maximum data set minus the minimum data set or data value. For the Cleveland Cavaliers, that's 81 minus 77. This is equal to 4 inches. For the Golden State Warriors, the range is equal to 84 minus 71, which is equal to 13 inches. What do the results for each team indicate? So the averages are the same of heights are the same, but the ranges vary by, so I could say the ranges vary by 13, subtract 4 is, the ranges vary by 9 inches. All right, so that's how I would sum up that data. So that's how you would calculate the mean, and that's how you would calculate the range for a data set. Are there any questions on calculating the mean or range? Yes, that's no. All right, so let's jump over to standard deviation. So here's a equation for standard deviation. The standard deviation refers to variation around the mean. It can never be negative. It can be 0, but only if all the data points are exactly the same. Standard deviation increases dramatically if there are outliers. Larger standard deviation equals higher variation. The units are the same at the original data points. I think that meant they mean to say here as the original data points. Okay, so the mean, here we have the standard deviation formula. So it's just basically the square root of the number of data points, and then we sum up all of our x's squared, and then we subtract the sum of all x's, and then we square that, and we divide by the number of all of our data points, multiply by the number of our data points, subtract 1. So example 1, using the following pulse rates of males, all in BPM, calculate the following. So the mean. So we have 84, 74, 50, 60, and 52. So how do we calculate the mean? We know that the mean is equal to x bar. I'm just going to x bar is equal to the sum of all x's divided by the number of x's. So let's just sum up all the x's. So that's 84 plus 74 plus 50 plus 60 plus 52 equals 320 divided by 5. So 320 divided by 5 equals 64 beats per minute. Remember to include your units. So the standard deviation. So in order to calculate the standard deviation, we're going to have to square our x's. So I'm going to create a little table here of x squared. So x squared is 84 squared is equal to 7,056. 74 squared is equal to 5,476. 50 squared is equal to 2,500. 60 squared is equal to 3,600. 52 squared is equal to 2,704. Now we're going to sum all of those x's up. So 7,056 plus 5,476 plus 2,500 plus 3,600 plus 2,704. To sum all of that up is 21,336. So that's the sum of our x's squared. So now in order to use our standard deviation equation, we're going to have to sum up all of our x's as well. So 84 plus 74 plus 50 plus 60 plus 52 equals 32 or 320. So the sum of our x's is equal to 320. So let's bring that all into our equation. So our equation is equal to n. So the number of x's is 1, 2, 3, 4, 5. We have 5 pulse rates. So that's 5 right here. 5 times 21,336. Subtract 320. And then we're going to square 320. And then we divide it by n, which is 5, multiplied by n times 1, or n subtract 1, which is 4. Then we're going to find the square root of whatever that is equal to. So 5 times 21,360 is equal to 106,680. So 106,680 subtract 320 squared is equal to 102 bracket or comma 400 divided by 20, and then we're going to find the square root of that. So this equals 106,680 subtract 102, 400. So this equals 4,280 divide by 20, and then we find the square root. 4,280 divide by 20. Just going to take you through stepwise how to do this. So this is 214. Square root of 214 is equal to 14.62. Or I can actually round that 2 up. So I'm going to say 14.63. And in statistics, we like to keep a couple extra decimal places. So I'm going to say 14.63. And then, of course, standard deviation has, the units are the same as the original data points. All right, so we're going to keep the units BPM, beats per minute. All right, so that's how you solve for the standard deviation. It is a lot of work. There's lots of big numbers, so that's why you need the practice. And I believe I posted the homework for week number 4, and I also posted the homework for week number 3, just so that you get enough practice before your first exam. All right, so that's how you calculate the standard deviation for ungrouped data. And it's very important to know the formula on the formula sheet. All right, Any questions on standard deviation calculations?
No.
No? Okay. All right, so the mean weight. Let's calculate the mean weight of the varsity football team here. So example 2, the following data represents the weights of competitive athletes on a varsity football team, all in pounds. Calculate the following, the mean weight. So the mean weight is calculated by the sum of x's divided by, the sum of all x's divided by the number of x's. So I got that formula from this sheet right here is the first formula. Yeah, it's posted on Moodle. It's posted underneath the assessments. So Rihanna, here I'll show you where it's posted. So the formula sheet is posted. So if I go to the meta shell and I go right to under the assessments toggle, it's posted right here. So the formula sheet for your exam is posted right there under exam number 1. Okay. And that's where your exam will be posted when on February the 10th. So that's next Wednesday when you're writing your exam. I'll be posting it right here. And the outline for the exam is there as well, as in what to expect on the exam. Okay, so back to where we were. Okay, so in order to calculate the mean of all these weights, what we're going to do is add up all the weights and then divide by the number of weights. I already know there's 11 because I counted it out. But for those of you who don't know, you should count it out right now. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 weights. And we're going to add these all up. So 189 plus 254 plus 235 plus 225 plus 190 plus 305 plus 195 plus 202 plus 190 plus 252 plus 305 equals 2,542. And then we're going to divide by the number of numbers that we have, which is 11. So 2,542 divided by 11 equals 231.09 lbs. So that's the average weight of the football player in this list of weights. That's the average weight. The standard deviation, so we're going to have to come up with that x squared table. So I'm going to write a list of all the weights, and then we're going to come up with the x squared table right beside it. So all the weights are going to be listed here. So 189, 254, 235, 225, 190, 305, 195, 202, 190, 252, and 305. All right. So now we're going to square all those x's. So 189 squared. So I'm going to actually show you a faster way of doing this using Excel. So I've already opened up my Excel spreadsheet and I'm going to share that with you. So I'm going to use Excel to actually calculate this. So what we could do is just actually enter all of the weights into Excel. So we're going to have 189 plus, and I'm just going to enter all of the weights into my Excel spreadsheet, 254, 235, 235, 225, 190. So when you're dealing with massive amounts of information, sometimes it's not efficient to calculate by hand. It's more efficient to calculate using Excel. So 189, 254, 235, 225, 190, 305, 195, 195, 202, 190, 252, 305. All right. And then in order to calculate the standard deviation, it's important to know the formula. So the formula is equal to STDEV, open bracket, and then you select all the information that you'd like calculated. Now this is much faster than doing it by hand. And the standard deviation is equal to 43.85999. So that is the standard deviation. It is equal to 43.899. So how did we calculate that? We calculated it using Excel. It's much faster and it gets you to what you need. So the formula in Excel is equal to STDEV, and then you open bracket and then you select all the cells that you need, and then you close bracket and you press enter. And that's how you calculate using Excel. It's much more efficient than having to use a calculator. All right. Population parameters for standard deviation. Are there any questions on how to calculate the standard deviation of data using Excel?
Can you say that code one more time?
So the code is you press equals, so equals STDEV, open bracket, you select all the cells that you'd like to calculate the standard deviation of, close bracket, enter.
Thank you.
Yeah. Okay. Excel is much faster than doing any calculation by hand. So I would definitely recommend Excel. Okay. And if you want to do it by hand, then you need to know how to use this formula. And so the way that we could use this formula is, so what I could do is actually use Excel to use the formula. So what I would do is I would actually insert, so I'd call this X, and I call this X to the power of 2. So this is what I'm going to do, is actually square all of the X's in this formula. So what I could do is square all of these X's. That's what the most time-consuming thing is actually this multiplied by itself again. So I would have this massive table of all of these values multiplied by themselves. And then I'd have to sum all of that up. So this would be equal to the sum, open bracket, the sum of all of these, close bracket. So in order to work this Excel formula, you need to calculate this massive number. And so it's very difficult actually to calculate using Excel. But so, okay. So essentially what I just did was I found, I squared all of the weights using Excel. So I did A2 times A2, and then I just summed it all up to solve for this part of Excel right here. So the sum of X squared. So I could actually calculate this for my football players. So what I would do is S equals 11 times 600, 6,670, subtract the sum of all of my X's squared. But it would take a very long time to calculate that. But I think that I should actually show you how to do it. So I'm going to actually open up another page and show you how to do it. Okay. So okay, so I'm just going to write down the formula and then I'll show you how to do the calculation. So the sum of the x's squared, subtract the sum of the x's squared, divided by n, subtract 1. So we know n is equal to 11. We know that, whoops. We know that the sum of the x's is equal to sum of the x's squared is equal to 606 times 606,670. I just calculated that using Excel. Okay, and then so what I'm going to do right now is using Excel, I'm actually going to sum up all of my x's. So now I have 2,540. So the sum of the x's is equal to 2,542. So now I can actually work with that. And I can actually solve for my standard deviation using the longhand calculation. So this is going to be equal to 11 times the sum of the x's squared, which was 6,600, 670, subtract 2,542 squared over 11 times 10. So this is equal to, and then I'm going to have to square root that at the very, very end. So 2,542 squared is equal to 6,461,764. 11 times 606,670 is equal to 6,673,370. And then we divide that by the square root of 11 times 10. So 6,673 and 6,673,370 subtract 6,461,764 equals 211,606 divided by 11 times 10, which is 110. Oops. And this is equal to, and then of course we're going to square root this. So 211,606 divided by 110 is equal to the square root of 23.69. So the square root of that is equal to 43.856, which is what we already found using Excel. So that's the standard deviation written out the long way, but we already actually found that using Excel. So using Excel, instead of doing it the long way, what you could just do is equals STDEV, open bracket, and then just highlight all of the different football player weights, close bracket, and then you get 43.8599, or you can calculate using the long way and you can get 43.856 using the longhand calculation. So which one do you prefer? Type that into the chat. Do you prefer a longhand calculation or do you prefer Excel? Yeah, so I think a lot of people are voting for Excel. I don't think many people are voting for the longhand calculation. So I'm going to be showing you how to do Excel from here on out because I don't think anybody is really voting on how to do the longhand calculation because it throws you for really big numbers and it's really easy to make a mistake. So some people like the longhand, but it's quite easy to make a mistake. Excel is actually just so much easier. You just input the numbers and then you type in the formula and then you just hit enter, and it takes like less than 2 seconds to do. So all right, so let's go back to our notes. Was somebody about to say something there? I thought I heard someone. Okay, so let's go back to our notes.
I do have a question though. Isn't there 2 standard deviation formulas for Excel? One's for population and the other one, I don't remember. It's a different letter.
Yeah, so it's STDEV open bracket, and then you just select what you'd actually like to find the standard deviation of. So that's the formula that you need to remember, is this one right here, STDEV open bracket, and then you select what you need to find, and then you do close bracket, and then you hit enter. Okay. So I just illustrated 2 different formulas. One's really hard, one's super easy. So I think, or one method's easy, one method's very hard. So it's really up to you which one you'd like to use. But both of them should get the same answer. All right, so population parameters for standard deviation. The formula for population standard deviation provides a different answer than the formulas for samples. Population standard deviation is calculated as follows. Sigma equals the square root of the sum of x minus mu squared divided by n minus 1. This formula is not on the formula sheet, and you will not need to calculate it. You will be given population standard deviations directly in the question. All right, so the next topic is called statistically significant values. And I can't illustrate this enough how important this is. Any values between the mean plus or minus 2 standard deviations will be in the center of normal distribution curve and will be considered common or expected measurements for the data set. So it's really important to know that any values that are within 2 standard deviations, so here's 2 sigma minus 2 sigma of the mean. The mean is right here in the center. And then this is plus 2 sigma. These are statistically significant. And then anything greater than this is statistically high. And anything here is statistically or unusually low. So you could say unusually high. These values that are anything greater than plus 2 sigma is unusual. And then anything that unusually high, and anything less than 2 sigma from the mean is unusually low. So there's going to be lots of questions on the exam on, is this unusually low or is this value unusually high? And what you need to do is calculate whether or not a value is less than or greater than 2 sigma from the mean.
Miss, were you supposed to be screen sharing something?
Yes, I am. Yeah. Okay. So any values between the mean plus or minus 2 standard deviations will be in the center of the normal distribution curve and would be considered common or expected measurements. So anything within 2 standard deviations right here would be considered expected or common. Anything less than 2 standard deviations from the mean is going to be considered unusually low, and anything greater than 2 standard deviations from the mean is going to be considered unusually high. So there's going to be questions like that on the exam. They're going to say, actually, you'll see it when we get there. So is the value unusual? Any values equal to or less than the mean minus 2 standard deviations are considered unusually low. Any values equal to or greater than the mean plus 2 standard deviations are considered unusually high. To determine whether or not a value is unusual or significant, X bar plus or minus 2 standard deviations, or mu plus or minus 2 standard deviations. Okay, so I'm going to go back up here and we're going to determine what would be considered unusually high pulse rates for males. So what I would do here is I'm going to say anything unusually low would be the mean minus 2 standard deviations. So the mean is 64 minus 2 standard deviations is 2 times 14.63. And this is equal to equal to 34.74. Oh no, hold on a minute. That doesn't make sense. I'm gonna have to erase that. You'd make sure you do the bed mass first. So 2 times 14.63 equals 29. So 64 minus the answer equals 34 beats per minute. So anything less than 34.74 beats per minute is going to have an unusually low beats per minute. So less than 2 standard deviations from the mean. Anything unusually high is going to be basically the mean plus 2 standard deviations. So 64 plus, and then I'm going to do brackets, 2 times 14.63, close bracket, 93.26 beats per minute. All right, so that's unusually high and unusually low based on this information. How about, did we calculate the mean and the standard deviation? We calculated the standard deviation and the mean here. How about the mean and standard deviation here? So what would be unusually high and unusually low weight for this football team? Unusually low would be equal to our mean minus 2 standard deviations. So this equals 231.09 minus 43, or it's actually going to be 2 times 43. And then that's equal to 231 minus 2 times 43.899. So any number like 143.202 would be considered unusually low for this football team, and unusually high would be equal to X bar plus 2 sigma. So that would be equal to 231.09 plus 2 times 43.899. So 2 times 43.899 plus 231.09 is equal to 318. Anything greater than 318.88 pounds. And I want to make sure that I'm saying less than 143.202 pounds. So that's how we determine whether something is unusually high or unusually low. So example 1, for a given data set of over 150 resting heart rates, the mean is 69.6 beats per minute, with a standard deviation of 11.3 beats per minute. What values would be considered unusually low? So I'll give you a minute to think about that. So what values would be considered unusually low? Right, so it's going to be x bar minus 2s. So remember what x bar is. X bar is equal to 69.6 minus 11.3. But remember that the 11.3 actually has to be multiplied by 2 first. So bracket 2 times 11.3. And what is that equal to? You can type that into the chat when you know what the answer is.
It's 47, so anything under 47 would be unusually low.
Yes, that's correct. Yeah, anything under 47 would be unusually low. Anything less than beats per minute would be unusually low. Okay. Okay, and what values would be considered unusually high?
It comes up to 92.2. So would it be anything over 92.2 or would it be 94.2 and over?
Sorry, so you said it was equal to 92.2, so
Yeah.
so 90, so let me just check here. Plus 69.6 equals 92.2. So it's anything equal to or greater than 92.2.
Okay, thank you.
Yeah, anything over 92.2. Okay, so is the resting heart rate of 95.2 unusual? Type that into the chat when you've given that some thought and you know the answer. Yeah, I see that somebody raised their hand. Go ahead. Okay, so 95.2 is unusual. That's correct. It's unusually high because it's greater than, so 95.2 is greater than x bar plus 2s. So therefore it's unusually high. Okay, what about, is the resting heart rate of 47.0 unusually low?
Yes.
Yeah, so it's 47.0 beats per minute is equal to x bar minus 2s, so it's unusually low. Yeah, that's correct. Okay. So it is unusually low. The reason why is it's equal to, so remember it says right here, so anytime a value is equal to or less than the mean, minus 2 standard deviations, then we're considered unusually low. So it's equal to 47 in this case. So that means that it is unusually low. So yeah, in this case it is. All right. So variance. Variance is a measure of variation obtained by squaring the standard deviation. The notation is very simple. Variance is equal to S squared, or population variance is equal to sigma squared. The units for a variance are the original units squared. Because the units are different from the original data, it is much easier to interpret and work with standard deviation rather than variance. So that's all that's mentioned about variance, is that all that we do is we take sigma and we just square it, or we another way of saying square is multiply the value by itself, or so you times it by itself once. So like a number multiplied by itself. Okay, so that's what variance is. All right, so let's jump into the next set of notes and we'll see what we have in store. So what we have in store here is another equation. So this is an equation that is used to find the standard deviation for a frequency table. So these are frequency tables right here. So standard deviation for a frequency table. For data in a frequency distribution table, calculating standard deviation requires adding columns to the table. The formula for standard deviation for a frequency table is, so we need the standard deviation. The standard deviation is equal to the sum, okay, sorry, I just was distracted there for a second. The standard deviation is equal to the square root of the number of data points that you have in total. So that would be the sum of all the frequencies. So you have to add up all the frequencies. And then multiplied by the frequencies times their x, which is the midpoint. And then we have, so it's basically this giant formula. So we need to break it down into steps in order for it to be more manageable. So what I do is I always bring out an Excel sheet, and it's just more easy to work with the data. So calculate the mean and the standard deviation for the following data. So first of all, I think it's really important to find our formula sheet and to find, okay, how do we determine our mean? Give me 1 second here. I just need to find something. Okay. So how do we determine the frequency, the mean for a frequency table? Sorry, I just have a couple of windows open that are kind of bugging me right now, and I just need to close them and just get more organized here. Okay. So we know that the mean for a frequency table is equal to this equation right here, right? So that's how we're going to find the mean for this frequency table. So let's write down our equation. The mean is equal to the sum of the frequencies times x divided by the sum of the frequencies. I believe that's the correct equation. Let me just double check. Yes, it is. Okay, but our standard deviation equation is right here as well. And we need to figure out how to work with it. So what I do is I actually work with Excel, and I know some people don't like working with it, but I think it's a lot faster. So I'm going to show you how to work with it. So what we do is we're going to find our midpoint. So we're going to have our lower class of our interval, and we're going to have our upper class of our interval. Okay. And we're going to set it up like this, and then we're going to find our midpoint, which is actually x in the formula. That's what x is. It's the midpoint. And then the lower class is 50.
Are you supposed to be sharing the Excel page?
Yeah, just 1 second. Can you see it now?
Yeah.
Okay. 50, 70. So I'm just entering all my lower classes right now. 110, 130. So I'm entering all of my lower classes. Now I'm going to enter my upper classes, or my upper classes of my intervals. So these are all on the right-hand side of my IQ scores. So my upper class is 69, 89, 109, 129, and 149. My midpoint is equal to the sum of this lower class plus the upper class, and then we're going to divide by 2. Whoops, that didn't work out so well. There we go. So it's somewhere smack dab in the middle between 50 and 69 is 59.5. I'm going to take my black arrow and I'm going to drag that formula all the way down because I'm going to use it over and over and over again for every single row. It's going to be used again. Okay. So now I'm going to start to try to tabulate what this formula is asking me to do. So I need to take my x and I need to square it. So that's another thing. But I'm actually going to take my frequencies and I'm going to multiply it by my x. So here we go. So frequency, all of my frequencies are listed in my frequency table right over here. So my frequencies are 2, 33, 35, 7, and 1. So all that information is already given and it's provided in the table. Now I need to start calculating the information on in the formula. So my frequency multiplied by my x is something I need to calculate. My frequency multiplied by my x squared is something else that I'm going to need to calculate. Okay, so now I'm just going to multiply these two columns together. So my frequency is equal to this column right here multiplied by, so that's an asterisk, multiplied by my x is this column right here. And I'm going to find my black plus sign and I'm going to drag it all the way down. And then so that'll give me my frequencies times my x. Excellent. So what about my frequencies times my x squared? I still need to square my x. So what I'm going to do in this column is I'm just going to find x squared. So all I'm going to do is take x and multiply it by itself. So x is right here, and I'm just going to multiply it by itself. And you can do that very easy. And it saves you a lot of time by getting Excel to do all these calculations for you. And so I drag it down with my black plus sign. And so that's the way I calculate my x squared. So to calculate my frequencies, I'm just going to take a drink of water. I'm just getting a little thirsty. Okay. So to calculate my frequencies times my x squared, all that I have to do is multiply this column of frequency, multiply by my x squared, which is this one right here. And then I drag that down with the little plus sign all the way down. So now I'm practicing how to generate these values in the equation. So now I need to sum this up. So I'm going to format this table a little bit, and I'm going to put a line at the very top part of my box, or top part of my summation line, and I'm going to total up all my frequencies. So I'm going to sum them up. So this will be equal to the sum of all of my frequencies. So that's what n, I'm actually calculating what n is equal to. So I'm going to say n is equal to right here. And then I'm going to say, what is the sum of all my frequencies squared? So the sum of all my frequencies squared, which is this part of the formula right here. So I'm going to sum that up right here. This is the sum. The sum goes like this. I highlight all of the cells and I close that up, and then it gives me the sum of that squared. F times x squared, the sum of f times x squared is right here. And then I'm going to have to find my frequency times x value, which is right here. And that's going to be the sum of all of the f times x values. So you can tell how this saves a lot of time if you know how to do it properly. Then you're going to find this value times itself, because see how we need to square the sum of f dot x, we have to square that value. So I'm going to basically take this value and multiply it by itself. Okay, so now in order to do all these equations, what I need to do is take n, which is 78, and I'm going to multiply it by f dot x squared, by the sum of f dot x squared, which is this value right here. I'm going to take that value which is 53 million, and I'm going to subtract it from the 51 million, which is f dot x squared, and that gets me about 1 million. So I'm going to have 1 million divided by 78 times 77. So I'm going to have this value right here, 1 million, approximately 1 million divided by, and then I'm going to close my bracket and say 78 times, and then n minus 1 is 77, close bracket, and that's 210 or 217. So what I can now do is say square root, because that's the very, very last step, is to find the square root of it. So the square root of 217, and then close that bracket, is 14.67196. So now I know what the standard deviation is of 14.196, if I'm not mistaken. So that's how, or 14.7619, 14.7619. All right, so that's how you would find the standard deviation using Excel. Trust me, it's a lot faster, and it's once you're able to use all these cells, it's much faster than trying to calculate by hand. But calculating by hand, it takes probably twice as long to do the calculation. But it's worthwhile knowing how to do both. But just doing it with Excel is it's just another tool in the toolbox to help you calculate things a lot faster. So let's now, there's another thing that I wanted to do, and that's to calculate the mean. The mean, actually, so before we switch over to mean, are there any questions on how I did the Excel calculation? I mean, it's a lot to hold, it's a lot to digest, but as long as you follow how to get the midpoint, how to get the frequency, and then how I summed everything up. And it's also a matter of interpreting this formula, right? Okay, it's a sum of f dot x squared. It's a sum of f dot x, and then you square, right? So it's an important tool to have, and perhaps you want to review this again and again, but I did post some videos, and I'll show you where I posted those on the class meta shell. So if I should be sharing my screen with you. So my screen, if you go into the meta shell and you actually look on week number 4 and you go week number 4 notes and you click on that and you go to the YouTube videos actually walk you through step by step how to do this using Excel. So the YouTube video, like if you click on this Word document, there's YouTube video on how to find the standard deviation of a frequency distribution table. There's, I think, 1, 2, 3. I have 3 different examples of that so that you can actually follow along and watch those YouTube videos if you like. That's something that can help you out. Okay, so back to where we were. Okay, so are there any questions on how I calculated the standard deviation? It's 14.76196. All right, so now we're going to calculate the mean of this frequency distribution table. And what we need to know is our midpoints. So our midpoints are basically, I actually just calculated them right here in the Excel spreadsheet. So it's the lower class plus the upper class divide by 2. That's how you calculate the midpoint. So it's 59.5, 79.5, 99.5, 119.5, 139.5. So I calculated all the midpoints, and so that's what X is in the formula, right? Is the midpoint. Remember, midpoint equals X in the formula. All right, so the frequency times the midpoint, so that's 2 times 59.5 plus 33 times 79.5 plus 35 times 99.5 plus 119.5 times 7 plus 139.5 times 1, and then we divide by the sum of all the frequencies, which is 78. I've already summed it up. It's right over here in the frequency table in the Excel spreadsheet. So, okay, so if we add up all of those together, so I could actually do that in Excel now, couldn't I? But I can use my calculator for this one. So 2 times 59.5 plus 33 times 79.5 plus 35 times 99.5 plus 119 times 119.5 times 7 plus 139.5 equals 7,201. And then we divide that by 78. So 7,201 divided by 78 equals 92.32. So that's our average for this frequency table. And we found it using this formula. All right, so we know what our average is and we know what our standard deviation is. So what IQ scores would be unusually low? I'm going to give you a minute to think about that. We know what our standard deviation is and we know what our mean is. What IQ scores are unusually low? And what IQ scores are unusually high? I'll give you a minute to calculate that. Okay, so what IQ scores are unusually low? Type it into the chat if you know the answer. All right, so Stephen says, sorry, let me find that chat again. Chat comment. 62.8. So how did you find 62.8, Stephen? Yeah, so how Stephen found those that value was IQ scores that are unusually low. They have to be IQ scores that are unusually low have to be less than basically x bar minus 2s. So that's basically 92.32 minus 2 times 14.76. So it's less than 62.8. So that's what the IQ scores have to be, is less than or equal to 62.8. And what about IQ scores? Yeah, so Stephen's saying less than, and then IQ scores that are unusually high, scores that are unusually high are greater than basically x bar plus 2s. So if we have the average is 92.3, plus 2s, so sorry, 2 times s. So we figured out what s is. S is 14.76, 14.7619, 14.76. So 2 times 14.76 plus 92.32 equals 121.84. Anything greater than 121.84 would be IQ scores that are considered unusually high. That's right. Okay. All right, thank you, Stephen. Okay, so now we have another frequency distribution table. We have calculate the mean and standard deviation for the following data. So what we could do is I'll walk you through how to do it in Excel, or we could do it without Excel. But we need to know the formula first. So I need to write this down. Okay, so just give me 1 minute here. Okay. Actually, I have the formula in the textbook. There it is. Okay, so let's calculate the mean. All right, we'll calculate what should we calculate first? The standard deviation. So the standard deviation is equal to the square root of the number of numbers, or the number of frequencies. So we're going to have to add up the sum of all the frequencies is equal to n. Just remember that. I remember that I had a hard time over the weekend when I was practicing because I didn't know what the n stood for. Times f times x squared, close bracket, subtract the sum of number f dot x square, close bracket, and then we're going to square this, divided by n minus 1. So let's calculate the midpoints first. The midpoints are 40 plus 54 equals 94. Divide by 2 equals 47. So that's 47 for a midpoint. 55 plus 69 equals 124. Divide by 2 equals 62. 70 plus 84 equals 154. Divide by 2 equals 77. 85 plus 99. Divide by 2 equals 92. 100 plus 114. Oops. 100 plus 114 equals 214. Divide by 2 equals 107. So first we need to find the midpoint, which is x. So that's how we would start this this formula, or start solving for the formula. But now you know what I want to do is I want to find the mean first. So I'm going to find the mean. Just basically x bar equals the sum of the frequencies times x divided by the sum of the frequencies. So x bar equals the sum of the frequencies dot x divided by the sum of the frequencies. So this equals 15 times 47 plus 63 times 62 plus 77 times 62 plus 92 times 11 plus 107 times 2. And then we divide by the number, or the sum of all frequencies. So the sum of the frequencies is 15 plus 63 plus 62 plus 11 plus 2 equals 153. So in order to calculate the mean, I'm going to take 47 plus 15 equals 62, or sorry, 47 times 15 plus 62 times, okay, let me try that again. 47 times 15 plus 62 times 63 plus 77 times 62 plus 92 times 11 plus 107 times 2 equals, so this equals 10,611 divided by 153. So 10,611 divided by 153 equals 69.35. All right, so that equals the average pulse rate for this frequency distribution table. Now, in order to calculate the standard deviation, I'm actually going to go over into Excel and do a very similar table as to the one I just did. So let's try another sheet. I'm going to create another sheet. And so I'll explain step by step how to do this again. So first we're going to generate our midpoints. So actually I already calculated the midpoints, but I'll say the lower class and then the upper class of our interval. And then the midpoint. Pulse rate, the lower class. So the lower class is always on the left-hand side of the interval. So there's 40, there's 55, there's 70, there's 85, there's 100. Actually, am I sharing the correct screen with you? I just want to make sure I'm sharing the correct screen. Can you see my Excel spreadsheet?
Yeah.
Okay,
Yep.
thank you. All right, and then the upper class is 54, 69, 84, 99, 114. Okay. Now my midpoint is going to be an average of these two values. So it's going to be the sum of this value plus this value divided by 2. So I've already calculated these values. So it should be 47, 62, 77, 92, and 107. Okay, great. The next column, now I need to start working this formula, but I'm actually just going to scroll up and work with this formula for now. My next column, I can put in my frequencies. So my frequency is 15, 63, 62, 11, and 2. So now I need to work with this formula right here. So I need to start solving for f dot x squared. So I'm just going to square my x. Why not square my x right now? So I'm going to square the x right here. So all that I'm going to do is this value C2 times C2. Enter. So that C2 times C2 is right here. And then the other value that we can do now is f times x squared. Okay, so what I can do here is the frequency times my x squared is right here. Oh, whoops. Frequency times my x squared. So I'm just going to make sure that I have my frequency multiplied by my x squared. And I'm going to drag that down with the plus, black plus arrow or black plus sign. And then I'm going to have my frequency times my x in this column because that's the next part of the formula. So is the frequency times the x. So why not do that one next? It doesn't really matter the order in which you do it on Excel as long as you plug them into the formula accurately later on. So the frequency is here multiplied by my x is here. All right. Now I'm going to have to sum up my frequency times my x, and I'm also going to have to sum up my frequency as well. So let's do, I'm going to, hold on a sec. I'm going to sum up my frequency. So let's sum this column up right here. So I'm just going to select the values that I want to sum up. So that's 153. Yeah. So that's 153. That's the value for n in this equation. And then I'm going to sum up my f times x squared right here. So that gives me my sum of f dot x squared. F dot x, or f times x, I can sum that up as well. So this equals the sum. And then I'm going to highlight all of these values and basically sum them all up. So now I have the summation of all of these So you know what I could do is a blended approach. So far I've calculated the sum of f times x squared. I've calculated the sum of f dot x. I've calculated n. So what I could do now is just plug them into the formula. So write them basically right beside. Just basically say this equals, 153 times the sum of f dot x squared is 758,907. Subtract 10,611 squared, square root this entire thing, divided by n, which is 153 times 152. So I could do that. Or I could finish it off in Excel. So that I'll do both for those of you who appreciate both of the approaches. So 153 times 658, 907 is equal to 16 million, or 116,112,771 divided by, or subtracted by 10,611 squared, which is 112,593,321. Then we're going to divide that by a very, very big number, 153 times 152. Well, it's not as big as the other ones. 223,256. And then we're going to square root the whole thing. So 116,112,771 minus 112,593,321 equals 3 million. Oh, I'm running into my other equation. Equals 3,519,450 divide by 23 million, or 23,256. 23,256 equals the square root of 151.335. This equals 12.3 as far as I can tell. So let's, I'm going to finish this up actually in Excel. I just need the equation. So the equation is, I need to basically square this value right here. So I'm going to square this value. So this equals this value squared. So this value times this value again. And then I'm going to take n, and I'm going to multiply it by f dot x squared. Okay, then I'm going to take this value and I'm going to subtract this value from the first. I'll get that value. Okay, and then I'm going to divide, essentially this value is going to be divided by 153 times 152. Oop, I think I must have made a mistake there. Oh yeah, I did. Okay, so basically I have to tell it to divide. So that's 151. And then I'm going to tell Excel to square root all of this. So square root 151. So now I'm telling it to square root. So now I get the standard deviation is equal to 12.3, and I just want to double check what I got over here. So I got 12.3. So now we have the X bar, we have the mean, and we also have the standard deviation. So now we can determine what values are unusually high and what values are unusually low, given what X bar is. So what pulse rates are unusually low and what pulse rates are unusually high, given that we have X bar and standard deviation? I'll give you a minute to think about that. Okay, so the pulse rates that are unusually low, can someone tell me how to calculate the pulse rates that are unusually low?
So you would take X bar and then you would subtract it by 2 times S. And then I got 44.75.
Okay, yeah, thank you, Sierra. Yeah, that's right. So 69.35 minus 12.3, or sorry, 2 times 12.3, 2 times 12.3 equals 44.75. So values that are less than 44.75 beats per minute. Okay, values greater than, okay, and values greater than, thank you, Sierra. And what are the pulse rates that are unusually high? Values greater than 69.35 plus, and then this would be 2 standard deviations. So remember, what we're doing is X bar plus 2 sigma would be pulse rates that are unusually high. So 69.35 plus 2 times 12.3 equals beats per minute. There we go. All right. So that's how we can determine if pulse rates are unusually low or pulse rates are unusually high based on a certain data set. All right. So now we're going to jump into measures of relative standing to finish off today's class. And this will be just wrapping up this unit, and then you're ready for your test, which is tomorrow at, not tomorrow, sorry, I didn't mean to say that, which is next Wednesday at 8:30 in the morning. There's going to be a test. And of course, you already know all about the outline and to study the outline, because the outline actually tells you exactly pretty much what's on the test. Yeah. Oh, 1 second, heart attack. Yeah, sorry about that. Yeah, so it's next Wednesday. So make sure you study that outline. It's really going to help guide you as to what's on that test and what you should pay attention into studying. And yeah, it would help you out a lot. Okay, so measures of relative standing. So we're on chapter 3.3 of the textbook. So please do the readings as well. Z-scores. So a Z-score is a value that represents the number of standard deviations from the mean for each data point. Each data value will have a different Z-score that tells you how many standard deviations plus or minus the value is from the mean. The Z-score is equal to X minus X bar over S, or the Z-score equals X minus mu over sigma. Recall that data equal to or beyond plus or minus 2 standard deviations is statistically significant, unusually high or unusually low. Therefore, data points with Z-score of plus or minus 2 or more are statistically significant values. Statistically low values, statistically are values not significant, or values significantly high values. So we have values that are on the lower end that are considered unusually low. We have values that are considered unusually high. And then we have values right smack dab in the middle that are considered not significant. The rules. The z-scores are always rounded to 2 decimal places because of the z-score table. There are no units in the z-score, and negative z-scores indicate that the data is lower than the mean. Positive z-scores indicate that the data is higher than the mean. All right, so example 1. In a sample of platelet counts, the mean was found to be 239.4 thousand cells per microliter, with a standard deviation of 64.2 thousand cells per microliter. The lowest platelet count in the sample group was 75,000 cells per microliter. Is this platelet count statistically significant? All right, so we're going to use the z-score for this, and we're going to calculate whether or not this is statistically significant. So z is equal to x minus x bar over s. So we know that the mean, or x bar, is equal to 239.4 thousand cells per microliter. And we know that the standard deviation is equal to 64.2 thousand cells per microliter, and the lowest platelet count of the sample group, or X, is equal to 75,000 cells per microliter. So I'm not going to include the units because Z is unitless. Is this platelet count statistically significant? So I'm just going to plug these numbers directly into the equation and see what we get. So this is equal to 75, subtract 239.4 over S, which is 64.2. So 75 minus 239.4 is negative 164.4. Divide by 64.2 equals negative 2.56. So yes, the platelet count is statistically low. So that's what that means, is that if the platelet count is statistically low, then that means that essentially, okay, so if our z-score is less than 2, then that means that yes, we have a significantly low value. All right, so that's what that means right there. All right. Any questions about the z-score and how we calculated it? Okay, so I hear no questions. Okay, so percentiles. Percentiles measure the location of a data point. Well, we already talked about this actually in week 2, but we'll go over it one more time. Percentiles measure the location of a data point within the ranked data. For example, the 50th percentile, P50, has about 50% of the data above and 50% of the data below this percentile. This means that P50 is the same as the median. Percentile value of X, number of values less than X. Percentile value of X equals the number of values less than X divided by the total number of values, multiplied by 100. Always round to the nearest whole number for percentiles. Example 1. The following table lists 40 cotinine values measures in nanograms per milliliter in smokers. The data is already ranked in order. Find the percentile for a cotinine level of 198 nanograms per milliliter. So first we have to locate where 198 is. So first I observe that 1, 2, 3, 4, 6, 7, 8, 9, 10. So it's all boxed off in tens. So first we have our first 10 here, 20 here, and then 21, 22, and then 23. So number of values less than 198 is percentile value of x. So I'm just going to call this p. Percentile is equal to the number of values less than. So this is 22. So there's 22 values less than, and the total number of values is equal to, there's 10, 20, 30, 40 values in total. Then we're going to multiply by 100. So 22 over 100 is equal to 55. So this is the 55th percentile of data ranked in this table is 198. So P55 equal. So actually I wouldn't say it that way. There we go. The percentile equals 55. It's the 55th percentile for 198 nanograms per mil.
So would you write it as P is equal to 55%, or could you just do 55?
Yes, so I would say, yeah, P equals 55 actually. Yeah, because it doesn't say multiply by 100%, it just says multiply by 100. So I would write it as 55. Yeah, thanks for
Okay.
pointing that out. Yeah.
Mhm.
Okay, quartiles. So quartiles are specific percentiles that are used to determine certain measures of relative standing, such as the interquartile range, the 5-number summary, which are used for box plots. The 5-number summary is the minimum value, Q1, the first quartile, P25, Q2, the second quartile, P50, Q3, the third quartile, P75, and the maximum value. If a quartile works out to be in between two data values, take the mean of these two data values. The interquartile range is calculated by the IQR is equal to the third quartile minus the first quartile. Again, if a quartile works out to be in between two data values, take the mean of these two data values. The interquartile range represents the range between the central data points that are close to the median. Okay, example 2. Using the same cotinine data from example 1, calculate the 5-number summary and the interquartile range. Okay. Okay, so first and foremost, we have the 5-number summary means that we need to calculate the minimum value, P25, P50, P75, and the maximum value. All right, so the minimum value is equal to 0. The maximum value is equal to 491. The P25, or the first 25% of the data, is less than the 86 nanograms per mil. Is it nanograms per mil? Is that what it? Yeah, nanograms per milliliter. The data that represents the halfway point is 167. So the way I'm looking at this is I'm looking at 10, 20, 30, 40. So the data that represents the 3/4 point range would be 250. So we've calculated the 5-number summary, and the 5-number summary is used to generate box plots, by the way, and we'll be talking about that in 1 second. So the interquartile range is basically, I'm just going to be applying this equation right here. So the IQR is equal to Q3 minus Q1. So Q3, so remember that Q3 equals P75 and Q1 is equal to P25. So Q3, remember, is 250 minus 86. So the interquartile range is equal to 250 minus 86. So that's 164. And then we could call that nanograms per milliliter because it probably has units. I think it does have units. Yeah, all of these would have units. So yeah, so all of these units are nanograms per mil. All right, so there's another way we can do this is we can actually graphically represent the 5-number summary, and the 5-number summary can be represented using box plots. So a box plot is a graphical representation of the 5-number summary, and it can be used to identify skewness, which shows up clearly on the diagram. So the procedure for making a box plot is first find the 5-number summary, draw a line segment from the minimum value to the maximum value, and draw a box extending from Q1 to Q3, and draw a line at the median, which is also known as Q2. So let's draw a box plot for this data value set right here. Okay, so this value right here would be the minimum, which is equal to 0. This value over here would be equal to the maximum, which is equal to 491. Oh, it's actually already drawn right below. Whoops. Okay. And then we would have Q3. Q2 is represented right here. So this would be 167, which is Q2. Q3 would be represented right here, which is 250. And then we would have our, or no, that's not Q2. That would be Q1, pardon me. Q1, which is 86. Q2, which is 167. Q3, which is 250. And so you can kind of tell that the data is skewed. I always draw a foot to let me know, or to guide me on which skew is actually happening. And so since all of the data is more off to the it's more off to, like, the center of the data is more off to the left, I can actually tell it that this is right skewed data because the median would go where the big toe is, and so that this is right skewed data. So the big toe kind of indicates where the data kind of goes towards. It's hard for me to explain this over the computer. If I was in person, it would be much easier for me to explain. But this is a right skewed data. So for example, the 5-number summary for the cotinine data, the box plot would look like this. And so since the right foot would be on this side, essentially this is right skewed data. It's very hard for me to explain that though over the computer. So interpreting box plots, look at the following box plot for rates of men and women, and what do the diagrams tell you about skewness in each of the data. So this one is a little bit easier, but this one is left skewed. This one is, so this one is left skewed. This one is right skewed. So if the box goes over to the left, then that means it's right skewed. If the box goes over to the right, then that means it's left skewed. I know it's almost counterintuitive, but that's kind of the way that the skewness works. And it's kind of hard to explain that one. So construct a box plot for the following data set of systolic and diastolic measurements in millimeters of mercury for 14 medical students at Bellevue Hospital. So the first thing I would do is actually order this information. So the first thing that I would actually do is I would take Excel and I would actually get Excel to organize this data for me or to sort the data for me. So I'd enter all of the millimeters of mercury or the blood pressures for these medical students, and I would sort it in Excel from least to greatest, 125, 120, 130, 130, 144, 143, 140, 130, 150. Okay, so that's how I would get Excel to sort this. So what I would do is right here, and I would go, oh, I don't know if it's sharing the right screen again. It doesn't do what I want it to do. Am I sharing Excel right now?
Yeah.
Okay.
Yep.
So I'm going to sort from least to greatest. So if you noticed how I did that, I'll just undo what I just did. So basically what I did is I highlighted the cells that I want to sort, and then I go over to here and it says sort and filter, and I can sort from smallest to greatest. And then what I can do is I can actually number the cells. So, oops. So I'm going to actually number my cells. And so I'd like this pattern to continue of numbering the cells. So I have 14 cells in total. And so my percentiles are going to be equal to this number divided by 14 times 100. So in order to find my 25th percentile, I'm actually going to have to take a mean between these two data points. So the 3 and the 4. So that basically, in order to calculate my Q3, I'm going to. Okay, so in order to calculate my minimum data point is equal to 120. My Q1 is equal to 125 plus 130 divided by 2. I'm going to have to do an average there because it's smack dab between the middle of these two values right here. My midpoint is equal to 130. My Q3 is equal to basically 75 percentile, which is equal to somewhere between this. So 140 plus 140 divided by 2, which the average between 140 and 140 is still 140. And then the maximum value is equal to 150. So in order to generate a box plot, those are the values that I would need. And then, okay, so here's some graph paper for me to actually generate my box plot. So I need to find the average between 125 and 130. 125 plus 130 equals 225 divided by 2 equals 127.5. So in order to generate my box plot, all right, in order to generate my box plot, I'm going to have 120 right here. So my minimum value is 120. My maximum value is 150. And I'm just going to guesstimate for now. My Q1 is way over here. So that's 127. I'm just going to try to wrap this up before my Q2 is 130. So it's about right here. And my Q3 is 140, so it's about right here. So that's how I would generate a box plot. So I'd actually have to label it a little bit. So I'd have to put in some numbers, and then I put 127 right here, 0.5, 127.5, 130, 140, And the skew is, again, I think it would be right skewed because the data kind of tails off to the right. So that, ladies and gentlemen, is the end of Unit 1. I guess we can have a preparation for the final exam for our next tutorial. So I think that would probably be the best use of our next session, which would be on, Thursday. So that would be the next use of our next session, is to get yourselves ready for exam number 1. And so please come prepared with some questions for me, because that would actually make the tutorial much more useful, is that if you had questions for me. So please take a look at some of those practice problems, take a look at the exam outline, start studying, do your best, forget the rest, and and make sure that you take a look at that exam outline. So I just want to, again, go through where it is. It's right on the Moodle page. So I'll just show you exactly where it is. It's under assessments, exam 1, and there's a exam winter outline, winter 21 outline. So if you go through it, you'll find an outline of the exam, what to expect. So there's no curveballs, there's no surprises. You'll know exactly what's going to be on it without knowing specifically what the questions are, but you'll know what type of questions and how many marks. So you know what to emphasize your studying on. All right, thank you for today's class. Sierra, do you have a question?
Yeah, are we allowed to use Excel during the exam?
I think so, yeah. Like there's no proctoring, so we can't really so usually under normal circumstances, the answer would be no. But since there is no proctoring, I would say yes. Yes, go ahead and use it.
Okay, I'm just wondering if we have to like show our work.
Yeah, like if you have to show your work, I think try to show your work as much as you can because there's a lot of marks awarded for that, especially if you perhaps you might get the wrong answer. And so it's really important to show your work so that part marks can still be awarded.
Okay.
So it's important to still show your work. Yeah.
Okay.
If you can.
I guess you could double check it with Excel or something.
Yeah, exactly. Yeah, double check it with Excel, or even if you're using Excel as a primary, still show your work if you can.
Okay, thanks.
Like try to use a blended approach, if that makes sense. Okay. So I'm going to sign out unless there's more questions.
Okay, bye.
Yeah, I have a question. I had printed out the beginning part of the slides, but is the second part of the slides where what we were just doing, is that in a different section?
No, it's here, I'll show you exactly where it is. It's on the same section. So if you go to week number 4 and you go week 4, it's called week notes E. Unit 1 E notes. That's the section that we were just doing.
Oh, okay.
Yeah.
Maybe I didn't print it out. All right.
Perhaps that might be it.
All right.
Okay.
Thank you.
You're welcome. Thank you. Any other questions?